Hi folks, welcome to our latest and likely final installment of our Bode plotting series. So what's going to happen in this session is we're going to talk a little bit more, finalize sort of some of our motivations for why we've gone through this, and then work some examples about with some particular transfer functions. All right, so first of all, again, why are we building all this structure? So think of our two-port network, right? So if we have a circuit that just exists inside of a box and it has an input and an output, so we can measure the voltage at the input and output. So this is our circuit C, right? And so we have the input voltage, VI, and we have the output voltage, VO, right? So we talked about computing the voltage gain, which is the ratio, right? If you remember, AV was going to be V out over V in. Now, we did these in the frequency domain, so those are generally complex quantities. And then we moved along in our discussion, and we ended up ultimately saying that we could recast that in something we call the transfer function, which is H of S. Okay, so the nice thing about that is we can break up our transfer function into various poles and zeros and constant gains. So we have these 7 components. If you recall, we would have a component 1 was going to be a constant, right? So we had some constant, we would call it K, and then 2 was a 0 at the origin, and then 3 was a pole at the origin, and then 4 was going to be a simple 0, 5 is a simple pole, 6 is a quadratic 0, and then we have number 7, which is the quadratic pole. All right, so it turns out that we can, because we can decompose H of S into a collection of one or more of each of these, we can take advantage of linearity of the system, which is something we kind of do intuitively. And so we can actually think of breaking H into several different subcircuits. And so we could draw that. Really, we could say, well, C is actually going to be thought of as a small circuit. We'll call it C1, right? So we have over here, we have our input, and then we're going to feed that into a subcircuit C2 and feed that, and we'll keep going all the way until we get to some final subcircuit. We'll call it Cn, and then we're going to have our output voltage there. All right, so each one of these things can be one of these things. And when we sort of stack them all together as building blocks, then we come up with the final transfer function. So what we're going to kind of do is take a transfer function, we're going to decompose it into these things. We can draw the Bode plot for each one of those individually and come up with the composite, which gives us the total response of the entire combination of circuit elements. Now, something to consider here is normally what we would do when we cascade from C1 to C2 to C3 and so on is we would be multiplying those gains together. And that's a convenient way to do it from an analytical perspective, but it turns out if we compute the gain value, right, each one of these transfer function elements could be thought of something that has a magnitude, right, and a phase, right? Each element is a complex number of some sort that is frequency dependent. Well, we would normally multiply the magnitudes together, but if we take them into dB, we can add So we're going to add the magnitudes. Let me clean that up a little bit. We're going to add the magnitudes in dB. Right? So remember, multiplication when we go to the log domain becomes addition. So that's what we're going to take advantage of when we're building our composite Bode plots. And that's why we've learned about each of these individual elements and sort of how they work. Okay, so to get to the heart of this, we're just going to start by working an example. So our first example is going to have the transfer function h of s equal 12 over s plus 3. Okay, so that's not a very complicated one, but what we're going to do is follow our rules to break it up into the various components that match one or more of those 7 elements. So the first thing we can do is we can say, well, that obviously equals 12 times something that looks like 1 over s plus 3. So you might think, well, 12 is our gain, but we've got to take that one step further. We've got to do something. We've got to divide out our pole, or our pole location here in order to put it in the form that we need. So that's going to be 12 over 3 onto 1 over, and I'm going to write it in the reverse order just because this is the way we talked about it, 1 plus s over 3. Okay, so now we have a gain term here, which is just 4, and we also have a simple pole at omega naught equals 3 radians per second. Okay, so how do we draw this? Well, first we're going to draw the gain. Okay, so we'll try to build a composite here. We'll do this, we'll just look at the magnitude first. Okay, so first thing I guess I should point out is that the magnitude, right, so this is just 4 unitless, which gives us 20 times the log base 10 of 4 is going to be about 12.04 decibels. Okay, so that's the constant gain. And so if we look at our axis here, all right, so we'll make a couple of marks on here. First of all, we're going to be interested in our omega naught, which is 3 radians. Well, let me back up a second. Just to plot the constant gain, we need to put something at 12 dB. So I'm going to go ahead and mark on this. I'm going to mark plus 10 and plus 20 dB. So this is our gain in dB. We have plus 10, plus 20. This is 0 down here. And then obviously I have minus 10 dB and minus 20 dB. Okay, so our gain of 12.04 dB, and obviously I'm roughing it here on this scale, but it's going to come in somewhere around here. Let me make these so we can see them. So I'm just going to put them in as dashed lines. That's actually the constant gain that we would be dealing with. So this is our 12.04 dB constant gain. It doesn't change with frequency. And then I've taken care of the gain or the magnitude for the 4, the factor of 4, or the 12 dB. And so now I'm going to talk about this simple pole. This simple pole exists at 3 radians per second. So I'm going to go ahead and mark this as 3 radians per second. I'm going to go ahead and say this is our omega. Now we're really plotting omega on a log scale, but we're going to label it, instead of with the exponents, we're going to label it with the actual value. So this is 3 radians per second. If I go 10 times higher in frequency, I would have, let me do that in another color here. So I would have 30 radians per second, and down here I would have 0.3 radians per second. So if you recall, for our simple pole, our straight line approximation is essentially going to bring us out along the 0 dB axis out to the cutoff frequency, or the break frequency. And so we'll say it would put us along here. And then it's going to roll off. This is a simple pole, so it's going to roll off at negative 20 decibels per decade. So that means by the time we go from 3 radians per second to 30 radians per second, we have to have dropped in magnitude by 20 decibels. Now this is just for this particular component, just for this simple pole. So we're going to live down here somewhere, and so then I've just got to push this dashed line through there as best I can. All right, so this is going to be negative 20 dB per decade. All right, so now since these magnitudes are on a log scale, I can just add them together to get the composite magnitude for the entire transfer function. If I didn't convert them to a log gain in dB, I would have to multiply point by point, which is much harder to do. All right, so now that I have that, I am going to draw the composite. Well, I have 12 dB up here, our constant gain, and I have 0 dB. So all the way out to our break frequency, I'm going to have something that's just going to track right along here at 12 dB, because I got 0 dB plus 12 dB. And then at the break frequency, something is going to have to change. So what's going to happen is now I'm going to just follow. This is going to remain constant, and this starts to dive here at negative 20 dB per decade. So I'm going to follow that at negative 20 dB per decade right down through here. Okay, so I'm going to go down at negative 20 dB per decade. Again, the best that I can with my artistic ability. So I'm going to say again, this is negative 20 dB per decade. And I started at roughly 12 dB up here. And then last but not least, we're going to say, well, that's sort of what happens, right? This is our straight line method, which is a good way to eyeball or approximate, which is a lot of what we're doing with our Bode plotting, because actually if we want higher fidelity plots, we're going to use a graphing tool, something like MATLAB or some other tool to produce it. But just for fun, I'm going to go ahead and try to draw the composite with a little bit of curve to it. What we do know, first of all, is that with this simple pole, when we actually encounter the break frequency, we would actually be about 3 dB low here. So we'd be at about negative 3 dB. So that means really our composite is going to pass through about 3 dB below that corner. And so then it comes down to me finding a way to draw this. Actually, I'm going to use maybe this color here that'll come through real nice. So I'm going to try to draw this composite that's going to come out. It's going to curve, and then it's going to dive down and asymptotically approach that. So that's essentially, the green line here is what the composite gain curve is going to look like. And this one here is the composite straight line approximation. So it's the composite straight line. Either one is fine. I mean, if you can tell my artistic ability, the lines aren't even parallel when they need to be and stuff like that. So this, again, is to give us a feeling for what this transfer function magnitude actually looks like in the frequency domain. And so obviously if we were designing a circuit and we needed a particular gain at a particular frequency, at least we'd have some idea what a circuit with this initial voltage gain structure is going to do for us. All right, so that gives us the magnitude. Next we need to look at the phase. Okay, so just for convenience, I've rewritten the transfer function. Notice I don't really have to write it in terms of j omega. That's something you can do if it makes you more comfortable, but really you'll learn if you do this very much, you don't need to do that. All right, so that's our transfer function, And now I'm going to go ahead and look at the axis for our phase. So I'll go ahead and draw that in. And again, this is going to be log omega, and this is going to be our 0 degrees phase. And I'm going to have negative 45 here and negative 90. This is our phase in degrees. All right, so first thing is I'm going to go ahead and mark our break frequency, right? So we had omega equals 3 radians per second, and I'll go ahead and mark our 30, and I'll mark our 0.3 radians per second. Remember, those are all important to us. And then we keep in mind, well, for our straight line approximation, there were a few points that were important. So one is we're going to have 0 degrees for a simple, before we get to the simple pole, our constant gain K here, it has a 0 degree phase. So it's just a scalar value with that's real. So it's going to have a 0 degree phase. So I could plot it on here, but we're going to be able to add the phases together in a similar way that we would add the magnitudes in dB. So I'm really not even going to bother to plot the phase for the constant gain. But I am going to plot the phase for the simple pole. So if you recall, the simple pole starts at 0 degrees phase. The straight line approximation takes us from up to 0.1 times the cutoff or the break frequency, and it's going to be 0 degrees up to there. We know that it's going to be negative 45 degrees at the break frequency, and it's going to be negative 90 degrees at 10 times the break frequency, and from there on out it's going to be flat. Okay, so I'll just go ahead and draw that, and then it's really just up to how well I can draw a straight line to connect these points all together, which I kind of did that there. It's actually pretty lucky for me. So that's going to be our straight line approximation. And then we know that in reality, that's not going to be exact. It's exact enough for most purposes. But just to remind you, really, we're going to sort of cut these corners a little bit. So it's going to do something like this. And again, that's not really good artistic quality on my part, but that's essentially what's going to happen. So that's going to be the phase response. It's going to roll from 0 degrees to negative 90 degrees over a span of frequencies that are centered about 3 radians per second in the logarithmic scale. Notice, right, this distance in frequency right here, let me use another color, right here, this distance is a decade, but it's actually only about 2.7 radians per second. And this distance is also a decade, but it spans 27 radians per second. So keep that in mind when you're on a log scale, that there is some sort of distortion here, but that's what makes actually these Bode plots work out. We're really, that's really one of the fundamental principles that lets it work out so well for us. So it lets us compress the frequency axis in a useful way. So that's our first example. And we'll go ahead and move on here in just a second to another example. I'm going to just show both the magnitude and the phase plot again here. So just give me a second. So as a reminder, that is the magnitude response for our transfer function. And this is the phase response for our transfer function. So now we'll move on to our next example. Okay, so for our second example, we have h of s equals 12s over s plus 3. So the only difference between that and the first one is we've added a 0 in the numerator. A 0 at the, yes, we've added a 0 in the numerator. A 0 by default or by definition is in the numerator, but it is at the origin. So we've added a 0 at the origin to this transfer function, and we're going to see that the frequency response is quite a bit different. So using the decomposition I had before, I can write this as something that looks like 12 over 3 again. I'm just going to break that out, times s, times something that looks like 1 over 1 plus s over 3, right? So no surprise there. So this is really sort of our 3 cascaded systems, right? I've got a constant gain. That's one system, so to speak. I've got a 0 at the origin. That's another system. And I've got a simple pole at omega equal 3 radians per second. So what I'm going to do is really look at the frequency response of those individually, and I'm going to add them graphically to form our Bode plot. Okay, so let's go ahead and dive right in to building that. First thing I'm going to do is look at the gain. Okay, so I'm going to be able to harvest a lot of stuff that we had in the first plot. So go ahead and draw. I'm going to go ahead and make this big. I'm not going to try to put both of these on one screen at a time because I think it's easier to make these less cluttered. So I'm going to go ahead and sort of keep them separated. Again, we're using omega in radians per second, and this is our gain in decibels. It's usually obvious from what's shown, but it's good to label things just to keep the confusion level down. Okay, so I'm going to go ahead and mark 10 dB and 20 dB, and I'll do the same thing below here. Negative 10 dB, negative 20 dB. All right, so I'm also going to go in and mark our break frequency. So it's going to be, again, 3 radians per second. So I can also come down here and have something that looks like 0.3 radians per second. And up here, a decade higher, as 30 radians per second. All right, so something else I need to be interested in is, that's for the pole that we have, the simple pole at 3 radians per second. We also want to mark, and I'll go ahead and just use this blue color here, the gain at 12 dB. This is for the constant gain. All right, so first we're going to deal with the 0 at the origin. If you recall, the way a 0 works at the origin is it always passes through 1 radian per second, and it's going to have a positive slope of 20 dB per decade. So that means we know if we get down from 1 down to 0.1, I'm going to go ahead and, oops, different color. I'm going to mark that here. 0.1, I should be down 20 dB, so I'm going to pass through this point. And then I also know if I get out to 10 radians per second, which I'm going to eyeball is right here, I should be up at plus 20 dB. So again, just eyeballing it, I should be here. Now this thing is going to just go forever at 20 dB per decade. So I'm going to try to draw that. It's going to go this way. And again, that's plus 20 dB per decade. Plus 20 dB per decade. And it's also going to continue down this way. Still 20 dB per decade. So it goes forever like that and passes through 1 radian per second. That's what a 0 at the origin does. And then the simple pole at 3 radians per second behaves exactly like what we saw in the previous example. So it would ride 0 dB all the way out to 3 radians per second. And then it's going to dive at negative 20 dB per decade. So if I look at my negative 20 line out here and I cross that with my 30 radians per second, then I'm going to say we must have to go through that line. So we're going to be going negative 20 dB per decade. Okay, so now what I have to do is marry those 3 gain traces together by adding them graphically. All right, so, well, the first thing I got to realize is if I think about this 0 at the origin that goes through 1 radian per second, right? It's not affected by this pole because the pole is 0 dB. So I add 0 and I stay with the same thing. But I am affecting it with this 12 dB constant gain. Okay, so really all that's going to serve to do, if I think about it, it's going to take this 0 gain line and move it up by 12 dB. Right, so let me get a color for my sort of composite shape. And so I'm going to move up 12 dB So that means if I were at negative 20 dB here, then I'm going to actually be at about negative 8 dB. Okay, and this, again, I'm going to eyeball this the best I can, and I know that I'm going to be up 12 dB when I get here, and so I'm going to traverse through this line. I guess I'm still going to draw through one of my labels, but it's going to put me there. Okay, so now once I hit this, nothing really changes. I'm going to continue on at a slope of positive 20 dB per decade until I get to this breakpoint. So I'm actually going to continue on until I get here. That's going to take me up there. And then at that point, I'm going to have, remember, my gain of 12 dB is constant, but I have something that's got a slope of positive 20 dB per decade and something that's got a slope of negative 20 dB per decade. So those are going to offset now, and I'm going to have, it's going to be flat. So I'm going to draw my waveform then. It's going to go out, and it's going to go right through one of my other labels, but that's okay. We're going to come right out like that. So our composite, and I'm going to go ahead and just leave the straight line in there, so I'm going to thicken that up a little bit. So it's going to go something like this, and then it's going to flatten out, and the gain will be flat for all frequencies above that. So that's what the composite straight line gain curve is going to look like in dB for the given transfer function. And if I felt like it, I could try to go ahead and put in something that would look like the break or the curve that I would have in there. And again, my artistic skill is not so good, but it might do something like that. And that's asymptotically going to approach that line. But again, I'm not an artist, so if I want fidelity, I'm going to put it into a computer. So that is the gain curve for our transfer function. And actually, you can do a little calculation. I mean, I'm a little off, but actually, if you compute what the gain would be at 3 radians per second, I'm probably going to be somewhere around 20 decibels. So I might be a little high in my graphics here, but again, you can check it with a computer. Okay, so now we're going to look at the phase of this transfer function, and I've gone ahead and written it out again here. And so we're going to draw our axis for the phase. And so in this case, I'm going to draw here. And again, my frequency, and put a label on here. It's just good practice. All right, so now, well, how is this going to be different than the other one? And really what's going to happen is, if you recall, for a 0 at the origin, we just have a constant frequency independent phase of 90 degrees. So let me go ahead and mark on my axis here. Let's go ahead and put 90 degrees, and then I'll go ahead and put 45 degrees, and down here 0 degrees. Okay, so I'm going to go ahead and for our constant gain, we have 0 phase, so there's nothing really to look at. So for our 0 at the origin, we're going to have a constant 90 degrees phase. Okay, so then we have our pole, our simple pole, which is going to look like what we had before. So I'm going to go ahead and mark a couple of things in here and just kind of give a hint of what it's going to be. But since we're adding these things together, remember what happened with the simple pole is that we would go out to 1/10 of the break frequency. So this would be 0.3, this was 3, and then we would have 30, right? So we would look at something that would come along here at 0, and then it would roll down and end up at negative 90. And I'm not even going to be able to show it on there because I didn't leave myself enough room, but that's okay. We do know that it would be at negative 45, so we'll put that here. Let me go ahead and mark that on the axis just so I can at least have some idea where I am. Right, so it's negative 45 degrees, and so we know that our straight line would come down like this. And it would actually keep going until we get to negative 90, and then it would flatten out. But really the point I'm trying to make is that this pole's phase response is just going to be shifted up when we add the plus 90 degrees associated with the zero's phase response that's constant. So that's going to really push us up to something that in the composite sense is going to come along at plus 90 degrees until we get to our break frequency, or I'm sorry, 1/10 of our break frequency. It's going to pass through 45 degrees at our break frequency, and it's going to make it back down to 0 degrees at 10 times our break frequency. Okay, so I'm going to go ahead and connect those and out like that. So again, that's our straight line approximation to our phase response. And if I felt, again, excited about that, I can go in and sort of try to put in a something that looks like it's a little more curvy. It's still got to hit this point here. All right, 45 degrees at the break frequency. So the blue trace here is going to be our total phase response for this transfer function. All right, so that's that for this example. We will move on to another example. Okay, for our third example, we're going to have the transfer function h of s equals 100, let's write that out, divided by s squared plus 25s plus 100. Okay, so we can tell by inspection that that's a quadratic pole. And also, because we know that we can actually write it in a form that looks like omega naught squared over s squared plus 2 zeta omega naught s plus omega naught squared, then I really can pull the information off of it that I need to know. So first of all, the important pieces of information are, one, that our the pole is located at omega naught squared equals 100, which tells me that omega naught equals 10 radians per second. And I can also look at 2 times zeta times omega naught equals 25, right? Because that's where this comes from here. And so I know that that equals 2 times zeta times omega naught, which is 10, which is 20 zeta. So I can solve for zeta equals the damping ratio. And that's going to be 1.25. All right, so I have a quadratic pole at 10 radians per second with a damping ratio of 1.25. So what's that going to look like? Well, if you recall, we know that the quadratic pole has a gain. So we're going to say I'm just going to summarize here, for omega much less than omega naught, right, our magnitude, so the gain in dB, let me write that properly, the gain in dB is going to be 0 dB, and the phase is going to be 0 degrees. And then for omega equal omega naught, my gain in dB is going to be 20 times the log base 10 of 1 over 2 zeta, okay, which equals negative 20 times the log base 10 of 2 zeta. Okay, and I know zeta is 1.25, so I can actually do that calculation and say that that's going to be approximately negative 8 dB. And the phase is going to be negative 45 degrees at that frequency. And then finally, for large frequency with respect to our break frequency, I'm going to have the gain in dB. So that's going to be 20 times the log base 10 of omega naught minus 20 times the log base 10 of omega. All right, so we have a constant minus something that rolls off at negative 20 dB per decade. And the phase at high frequency, so to speak, is going to be negative 90 degrees. Okay, so let's go ahead and draw this to get a feel for what's actually happening. Okay, so I'm going to try to put both of these on the same screen. So I'm going to start with the magnitude. Okay, again, this is our gain in dB. And we'll put 0 near the top here. Our omega scale. And I'm going to go ahead and mark our break frequency for this is going to be at 10 radians per second, right? So then I'll also have something at 100 and something at 0.1. And I'll go ahead and put negative 20 dB here and negative 40 dB here. So if you recall, our straight line approximation says that we're going to be 0 dB all the way out to the break frequency, and then it's going to roll at negative 40 dB per decade because it's a quadratic pole. Okay, so I'm going to go ahead and put that on here all the way out here, and then at negative 40 dB per decade, so at 100 radians per second, I should be a gain of negative 40 dB. So I'm going to go ahead and draw that. Again, that's my straight line approximation. Now, if you remember, when we looked at the actual gain, that is negative 20 times the log base 10 of 2 zeta, we looked at that gain at 10 radians per second, that we had something that was going to be about negative 8 dB. So that's going to live about right here. And so that tells us actually that's a point that the actual curve is going to pass through. And because our damping ratio is 1.25, this is a moderately damped system, and so we don't expect any kind of a resonant peak. So that makes sense. And so I'm going to go ahead and draw my more fancy curve that's going to come out and do something like that. So that's going to be what the gain does. Okay, so it's not really that sophisticated there, but it is important to understand. And so then, presuming that I could draw straight and parallel lines and such, which I appear to not be able to do, I'm going to go ahead and work on the phase. So again, so now I have, instead of a simple pole, I have a quadratic pole. So that means we're going to have a total phase change of 180 degrees across the frequency region of interest. So first let me draw the axes. So again, our phase, I'm going to go ahead and put 0 degrees up here. And so this is going to be 0 degrees. I'm going to go ahead and draw negative 90 and negative 180 degrees. And this is our phase. All right, so now, and I'll go ahead and mark, just to make it a little bit easier on me, the 0.1, 10, and 100 radians per second. All right. And so now, if you recall, what we need to have is we're going to go from 0 degrees. So I'm going to go ahead and put this in 0 degrees all the way out to 1/10 the break frequency. And then I'm going to be at negative 180 starting at 10 times the break frequency. And that's going to be constant from there on out. And then I want to connect these together. And I do want to make sure that I go through negative 90 when I'm at the break frequency. So it'll be something like that. All right, and so then we also can make a slightly better version. So we're going to try to freehand the curve. Something like that. That's the best you're going to get. That's pretty bad, I know. But anyway, I'm better with the straight line approximation, I guess. So for better quality, we want to use a computer. All right, so that is a third example. This is a quadratic pole at 10 radians per second with a damping ratio of 1.25. Okay, for our next example, I'm going to use the same transfer function I had before, except I'm going to modify the damping ratio. So I'm going to make it more lightly damped. So our transfer function is going to look like h of s equals 100 over s squared plus 2.5s plus 100. Okay, so this is going to have the same break frequency of omega naught equals 10 radians per second. And but now if I solve for the damping ratio, what I had before was 1.25, but this middle term before was 25. So now it's 10 times smaller. And so the only thing that can change in there, because my break frequency is still the same, means I must have a damping ratio that's 10 times smaller. So our zeta in this case is going to be 0.125. So this is a lightly damped quadratic pole at 10 radians per second. Okay, so let's go ahead and look at what happens. First of all, we want to think about, well, I'll talk about the gain here at omega naught in just a moment. But first, we're going to go ahead and just look at the magnitude response. So I'm going to start with our, again, our axes. And I'll put 0 roughly here. Again, logarithmic frequency. This is our gain in dB. I'll put 10 dB here. And then down here, I'll put negative 20 here and negative 40 down here. All right, and then I'll also go ahead and mark our important frequencies. So I'm going to mark 1, 10, and 100 like before. Okay, so this is 1, this is 10, and this is 100 radians per second. And now let's look at what the gain curve is going to look like. Well, we know that the general straight line approximation is just going to come out at 0 dB until we get to 10 radians per second, and then it's going to roll off at negative 40 dB per decade. That's going to look just like what we had in the last example. Okay, so I'm just going to draw it quickly here. We're going to come out from at 0 dB out to 10 radians per second, and then we'll roll off at negative 40 dB per decade. I don't know if I marked that on the last example, but this is going to be, I'll put it over here, negative 40 dB per decade. Okay, that's the straight line approximation. And we kind of left it at that. We looked at what the gain was at omega naught, and in this case, because zeta is different, and if we evaluate it at omega equal omega naught, we're going to find out that the gain, let me pick another color here, the gain at 10 radians per second, if we do our calculation, that's going to be 12 dB, a positive value, plus 12 dB, or something close to it, right? So that means it's going to be way up here. So we talk about this little peak type thing that we can just draw a line there just to remind us. But really what's going to happen is that the because of this lightly damped nature of this transfer function compared to the other, we're going to have this resonant peaky nature. So again, it's kind of hard to draw exactly what that curve is going to look like, but it's going to come out again at roughly 0, and then somewhere out here it's going to start to climb up. It's going to kind of hit that peak, and then it's going to roll down like this and finally go asymptotically to negative 20 dB per decade. So that's what the gain curve is going to look like. So we do have to, we can stick with the straight line approximation, but the problem here is we will miss this resonant peak, and this resonant peak is probably going to be important if this circuit is going to be operated anywhere around that 10 radians per second frequency. So that is something important to keep in mind. Okay, so now we're going to move on to the phase. Again, so let me go ahead and write the transfer function up here just so we don't forget what we started with. So we had h of s equals 100 divided by s squared plus 2.5s plus 100. And we know that our resonant, or our peak, actually a resonant peak, that frequency is going to be omega naught equals 10 radians per second. And we know that our zeta value is equal to 0.125. Okay, so because of that, we're going to see that the phase, it's going to do the same thing that the last one did. It's going to roll from 0 degrees to negative 180 degrees, but it's not going to do it quite the same way because of the small damping ratio. Okay, so go ahead and I'll draw the axes. Again, omega. This is our phase in degrees. All right, and I'll go ahead. This is going to be 0 degrees here, negative 90 degrees, negative 180 degrees. All right, so I'll mark the frequencies of interest. So we're going to have our 10 radian per second, 100 radians per second, and 1 radian per second. We know that we are going to, even with our straight line approximation, we know that we're going to be at negative 90 degrees at omega equal 10 radian per second. And from our straight line model, we know that we're going to come out at 0 until we get to 1/10 of omega naught. And at 10 omega naught, we're going to be at negative 180. And then we're just going to connect those. Again, that's our straight line approximation. Hey, I hit that pretty good. Kind of proud of myself for that one. All things being considered. But that's really not what's going to happen because of the resonant peak. So what's really going to happen now is we're going to have a sharper phase transition. It's not going to occupy this entire range of 2 decades. It's actually going to be sort of truncated in a sense, that it's going to come out at 0 and somewhere closer to 10 radians per second. And that's going to be dependent on actually what zeta is. That's where it's still going to cross at negative 90 at 10 radians per second, but it's going to turn, and let me fix that a little bit. It's going to turn and dive more quickly and then straighten out more quickly down here and go to negative 180. So it's going to be something more sharp like that. And again, the sharpness of that has to do with zeta. As zeta goes towards 0, that becomes sharper and sharper, or steeper and steeper, until finally it's essentially just a discontinuity at omega naught. So that is the phase response of this transfer function, and we see that it is different than the phase response from the previous example, and that's due to zeta being 10 times smaller. Okay, for our next example, we're going to use a slightly more complicated configuration here. So we're going to have h of s equals, in the numerator we have 3s squared plus 15s plus 18. And in the denominator we're going to have s squared plus 2.5s plus 100. So if you notice, that's the same denominator that we had in the previous, but the numerator has changed quite a bit. So it turns out that we can start factoring this thing, and one of the things we can do first, let's just look at the numerator. So the numerator we can rewrite as 3 onto s plus 2, and that onto s plus 3. Okay, and I'll go ahead and leave the denominator the same. S squared plus 2.5s plus 100. Okay, so we know that we can also now go ahead and factor a 100 out of the denominator, and at the same time we can modify our zeros in the numerator by factoring out those values, those corresponding values as well. So I'll write it out in detail. So we're going to have the 3 that we had before, and then from the s plus 2 we're going to factor out a 2, and we're going to be left with 1 plus s over 2, and then I'm going to factor out this 3, so we have another factor of 3 there, and that's going to be 1 plus s over 3. All right, so it looks like a lot going on there. And then I'm going to factor out the 100, and then I can write that as s squared over 100 plus 2.5 over 100s, and then plus 1. So we got some more work to do. I'm going to have an 18 now over 100, right? So I have 3 times 2, which is 6, times 3 is 18. That's where that 18 comes from. And I have the 100 there. And so then I'm going to have the same thing I had above there, 1 plus s over 2. That is my simple 0 at 2 radians per second. And I have another simple 0 at 3 radians per second. Right, and then I can reorganize in the denominator, just flip it around and say that's going to be 1 plus 2.5 over 100s, and then plus s squared over 100. So if I look carefully at what's going on there, I'm going to have my constant gain here. So I have this k equals 18 over 100, which is going to give rise, it's 0.18, that's going to give rise to approximately negative 14.9 dB. Then I'm going to have, like I mentioned, a 0. One of them is going to be at 2 radians per second, and the other one is going to be at 3 radians per second. And then I have my quadratic pole again, the quadratic pole. That's going to be omega naught equals 10 radians per second. And again, like we had in the previous example, zeta equals 0.125. And if we do a calculation just looking at the gain at 10 radians per second, and we're going to be concerned with that in a minute, is going to be approximately 22 dB, so something to keep in mind. So we're going to try to draw this, and this is going to be a little more involved. Okay, so to look at the gain, I'm going to give myself a lot of room to work here to keep things a little bit less cluttered. So I'm going to put my 0 dB line in midway up here. Frequency, I'm going to say this is going to be 20 dB, 10 dB. This is going to be gain in dB. And I'm going to have obviously 0 dB here, and I'm going to have negative 20 dB and negative 40. And then I'm going to mark a number of points of interest on here. So first of all, we'll go ahead and mark the 10 radians per second. So we're going to say 10 radians per second is here. So that's going to put 1 here, and it's going to put 100 up here. And we also have another one to be interested in. We've got something at 2 radians per second. So I'm going to mark that at about here. And I'll just mark 20 here just to be of interest. Then we also have 3 radians per second, which is kind of close by. And I'll go ahead and mark 30. And so now look at what's going to happen to each of these. So the first thing we're going to deal with is our constant gain. And so I'll go ahead and mark that if that gain is negative 14.9 dB. So that's going to be roughly here, negative 14.9. I mean, obviously that's negative 14.9, right? So that's going to come out here. Okay, so that's going to be our constant gain term. So we got to remember essentially we can draw all the others and then just remember to shift it down by 14.9 dB. That's another way to look at doing this. It just depends on what works for you. So I'm going to know now that my the 2 zeros, we'll go ahead and look at their straight line approximations. So the 0 at 2 radians per second, we would come along at 0 dB, and then at 2 radians per second, I would start climbing at 20 dB per decade. So that tells me at 20 radians per second, I would be at plus 20 dB. So I'd be roughly there. And so I'm just going to make a light marking here to take me up. And this would keep going, right, if it were by itself. And then I want to do a similar thing for the 0 at 3 radians per second. And so I'll pick the color up for that one. And we know that we would be at plus 20 dB at 30 radians per second for that one, right? So I would come along at 0. I'm not even going to bother tracing over for that, but I would come up at plus 20. Most of those slopes are plus 20 dB per decade. Right, and then the next one I want to do is the quadratic pole at 10 radians per second. So again, it's going to be 0 dB all the way out to our 10 radians per second, and we know that then it's going to, because it's a quadratic pole, it's going to have a slope of negative 40 dB per decade. So that means we need to be at 100 radians per second. We need to be out here at negative 40. And so that's going to come along and dive at negative 40 dB per decade. Like that, and keep going. All right, so those are all of the gain lines for the individual components, and now all we got to do is stitch it together graphically by eyeballing it. And when they get complicated like this, it's hard to do. Now there's one other thing that's going on is we also have, this is a lightly damped quadratic pole, so we're going to have a peak in the gain, a resonant peak that we've got to kind of deal with too. And we're just going to kind of eyeball that as well. So first of all, let's draw the composite straight line. We're going to be at negative 14.9 dB until we get to this point here. All right, so I can just go ahead and straight line it out to there. Then I'm going to start climbing at plus 20 dB per decade, but I'm only going to do that from 2 to 3 radians per second. So once I get here, I want to start climbing at a steeper slope. So I'm going to try to make this curve parallel to this 20 dB per decade slope. This is going to be hard to do, especially with my artistic skill, but it's going to do something like that. And then it's going to get steeper, and it's going to be climbing at 40 dB per decade, and that's going to happen all the way until we get to 10 radians per second. So I'm going to have a tough time trying to draw that and make it look decent, but I'm going to climb from 3 to 10 radians per second at 40 dB per decade. Okay, so, and I'm probably going to hit somewhere, let's say somewhere up about here. And that's probably not quite right. But anyway, that's going to look something. Those slopes don't look different enough, but we'll pretend they are. And then at that point, I'm going to have this 40 dB per decade increase compensated for by a negative 40 dB per decade roll off from the quadratic pole. So that means that I'm just going to get flat and be flat from there on out. So that's what the straight line magnitude curve is going to look like. However, the one thing I do need to remember is that my quadratic pole has a low damping ratio, so therefore the total composite is going to have a peak to it that's going to be at 10 radians per second. And if you recall, we did compute that the gain at that frequency is roughly 22 dB. So we're actually going to end up, we know the peak is actually going to take us up to about here. And so now I'm just going to eyeball something that at least looks reasonable. So I'm going to say, well, we're going to start at low frequency. We're going to be here at roughly negative 15 dB. I want to try to smooth off these edges here and come up and hit this peak. And then once I've come around the peak, I'm going to roll off here and kind of hit this asymptotically like that. So it's going to look something like that. And trust me, you'll get a lot better result if you try to draw it on a computer. All right, so now we're going to try to manage the phase. And the phase is also going to be a little bit difficult for us to handle. And so again, I'm going to give myself a lot of room to operate. And so first of all, I'm going to go ahead and draw the the phase axis here. I'm going to put 0 basically right in the middle. Omega phase in degrees. I'm going to put 180 up here, 90 degrees, 0 degrees, negative 90 degrees, and negative 180. So it's roughly symmetric. And I've got to mark some frequency points of interest. Now, because we got to deal with the quadratic pole and its straight line approximation for its phase transitions, actually for all of them, we're going to have to deal with a number of different frequency points. So first of all, we're going to put in the 10 radians per second right here. And so that's 10. I'm going to put in the 100 out here. No surprise there. I'm going to put in 1 here. Right? And then, so that's going to work for the quadratic pole. For the quadratic 0, no, I'm sorry, I don't have a quadratic 0. For the simple 0 at 2 radians per second, remember its break frequency is here. And so that means we got to be interested in something at 20. And we've got to be interested in something at roughly 0.2. Okay, so you can see where we're going to be a little more complicated. And then we got to do something similar for the simple pole at 3 radians per second. And my scale's not great on those. But again, these can get very hairy to try to do in a reasonable fashion by hand. But we really just want to be aware of the process. Okay, so I'm going to go ahead and do, I guess first we will look at what would happen for the quadratic pole. So we know that we're going to go from at 0 degrees up to 1/10 of the of omega naught. So we're basically going to be running along here. And then we know that we want to be at negative 180 when we get to 10 times omega naught. Again, because it's a quadratic pole, so it has to have a phase shift of 180 degrees. And we know that we are going to be at negative 90 at omega naught. Okay, so I'm going to do, again, my best curve fit through there. Not real great. I guess I didn't line up very well anyway, so that's actually a better point. And then this would be flat. All right, so that is our straight line approximation for our quadratic pole. Now remember, this is a lightly damped pole, so it's actually going to be scrunched up a little more than that. But we'll come back to that in a little bit. Okay, so now I'm going to deal with these simple zeros, and the way those are going to work is they're going to have a 90-degree phase shift, and it's the first one for the zero at 2 radians per second. I should end up getting to positive 90 degrees at 20 radians per second, and I should start at 0 at 0.2, and I should be at 45, which is going to be roughly here, at 2 radians per second. So again, do my best. I'm going to dot this one because there's going to be a lot going on here. And so I'm going to try to hit that, and then this will be flat from here on out. And I'm going to try to do something similar with the 3 radian per second. So it's going to have to hit those points. So it's going to come off here. Same essential slope here, but it's just behind in frequency, or higher in frequency. Okay, so those are our 2 dash lines. You can see this can be very messy. Obviously, graph paper and a straight edge and stuff can help you do this much better, but quite frankly, this is tedious. No surprise, especially with my artistic skill. So now, as you would probably expect, way out here at 100 radians per second, I have 2 positive 90-degree terms and 1 negative 180 degrees. So I'd expect those to roughly cancel. And so at 100 radians per second and higher, I'm going to expect my final phase to be somewhere around 0 degrees, which might not be something you expected. So if I want to start to draw the composite, now here's where I also want to pay attention to the fact that, and actually I'll draw that in here, that this quadratic pole is actually going to have a phase response that's going to come along at 0. Let me pick a better color for that. It's going to come along at 0, and then it's going to roll sharply. Actually more sharply than that even. Okay, so it's going to come along here and then sort of nosedive like that, and then straighten itself back out when we get down here. All right, so that's really what the phase is going to look like for the quadratic pole. And so now I want the composite of the dotted lines. So good luck to me for trying to draw that, but I'm going to give it a shot. So we're going to have something that's going to start out here at low frequency at roughly 0, and then it's going to start climbing. And remember, we've got to add these together. So we're going to add, we're going to follow the green dotted line, and then all of a sudden we're going to start ramping up at a higher frequency. And we've got to take a look at where we're going. So we're going to get up to something that's probably going to maybe around here. It's probably going to peak somewhere here above about 90 degrees or so. So I'm going to try to hit that, and then it's going to go through that, and then it's going to nosedive pretty quick back towards 0 because of the sharp transition here in the quadratic poles phase. And so, and it's going to, yeah, let's just say it's going to be kind of funky looking. So it's going to come up here, and then it's going to drive down pretty fast, and then live at about 0 degrees. And it's not going to probably be symmetric, even though I may have made it look that way. So it's going to come up here, and then dive pretty quick, like that. Again, hard to do by hand, easy to do with a computer. All right, so there is our phase response for the transfer function for this example, which included a simple 0 at 2 radians per second, a simple 0 at 3 radians per second, and this quadratic pole at 10 radians per second with a damping ratio of 0.125. Okay, for our final example, we're going to have a transfer function that looks like h of s equals 20s plus 5. I'm sorry, 20s squared plus 5 over s plus 8. Okay, so we can then do a little bit of work on that, and we can say, well, that's actually going to look like a 5 onto 4s squared plus 1. And then that's going to be divided by an 8 onto 1 plus s over 8. Okay, and then I can do a little bit more with that. So I'm going to say, well, that's going to be my 5 over 8. And then if I notice this 4 here on this quadratic term, I can actually write that as 1 over 4. Okay, so I'm going to say this is going to look like 5 over 8 onto something that looks like s squared divided by 1 over 4 plus 1. And that is going to be divided by my 1 plus s over 8. Right, so I'll put parentheses around that. Hopefully that helps. So what do we notice about this? Well, first of all, I do have I have a constant gain here of k equals 5 over 8. That's unitless, and that's going to give rise to about negative 4.1 decibels. Okay, so that's okay. That's my constant gain. That's easy to work out. I also have a simple pole. So a simple pole at omega equals 8 radians per second. Okay, so that's easy to see from that. And then I got to deal with this thing in the numerator. It's this s squared divided by 1 over 4 plus 1. Well, that's a quadratic term, right? The quadratic term would normally have an s squared, an s, and a constant term. And if you notice, the s term in there is gone. So what that means is that I have a quadratic, did I say a pole? It's not, a quadratic 0. The frequency for this quadratic 0 is going to be omega naught squared equals 1 over 4, which means that omega naught is 1/2 radian per second. Okay, and then since there's no middle term there, I know that zeta for this is 0. So this has no damping. And that's going to mean that we're going to have a peak in this 0. It's actually going to be headed in the negative, toward negative infinity. Okay, so let's plot the gain. Start with the axis. Okay, there's omega. Gain in dB. And I'll say that we'll end up with something around maybe 80 dB here. So we'll have 60, 40, 20, negative 20, negative 40. All right, so what are things of interest in here? Well, I know that I have a simple pole at 8 radians per second. So I'll go ahead and mark that first. Okay, so 8 radians per second. And that means I might be concerned with 80 radians per second. Right, so if it's a simple pole, that means that I'm going to dive at negative 20 dB per decade. So we're going to be at 0 all the way out to the break frequency. And then we're going to roll off at negative 20 dB per decade. So that means at 80 radians per second, I should be at negative 20 dB, and then I'll just continue on like that. So this is going to be negative 20 dB per decade. All right, so what else do I have of interest? Well, I have a constant gain. Let's not forget that. It's going to be a 5/8, so it's going to be a negative 4 dB roughly. Okay, so I'm going to go ahead and put that on there. Again, so it's negative 4 dB. That's going to be somewhere around here. And so again, I can draw everything else if I wanted, and then I can just shift by negative 4 dB to account for that constant gain. Okay, so now I'm going to deal with the quadratic zero that I have that's going to be at 1/2 radian per second. Somewhere about right here. And so that means I've got to have something that's going to be at roughly 5. That's 10 times that. And something that's at 50. And then I also may want to look at something at 0.05. Remember, this is logarithmic scaling. So just to get an idea of things. So what I'm going to do is I'm going to come out here to my 0.5 radians per second for my straight line. I'll come out to that. And then I'm going to go up at 40 dB per decade, because remember, this is a quadratic. So at 40, put a dot here. I'm sorry, not at 40. At 40 dB, I should be at 5 radians per second. 50 radians per second, I should be up at plus 80. And so I'll draw that. And it will keep going at plus 40 dB per decade. All right, so there I have all my composites. And so let's draw a few lines on here to help us keep track of things. So I'm going to essentially be at negative 4 dB until I get here. And then I'm going to start climbing at 40 dB per decade until I get here. And then this slope, it won't flatten out because it's going up at plus 40 dB per decade, but it will be offset by this negative 20. So that means the slope is going to essentially slow down, but it'll still increase without bound. Okay, so if I want to try to draw this composite now, again, good luck to me, but we're going to come out here, essentially at here. Then we're going to go up like this, and then we're going to decrease our slope to be something like that. Okay, now that's the way it would look, except we have to remember that we have zero damping. And so what that means is at this frequency right here, at omega equal 0.5 radians per second, my gain should be negative infinity. Okay, so I'm going to use this purple color. So really what's going to happen is this thing's going to come out here at negative 4 dB, and then it's going to take a nosedive here. And really it's going to try to go to negative infinity. So actually, let me fix that. Let me make that a little nicer. All right, so it's going to be a spike that looks like it just heads towards negative infinity. But then immediately after that frequency, it's going to pick back up and try to asymptotically follow this and then that. So that's essentially what it's going to look like. Okay. So again, hard to do these things by hand, but you get the idea what it looks like. That zero damping actually creates an asymptote there that we got to be careful about. All right, so now for the phase. The phase is actually not quite so bad for this because we're going to rely on the fact that we have zero damping. So we're not going to try to do the straight line approximation for the quadratic zero. We're going to rely on the fact that with zero damping, we're going to have a discontinuity in that component of the phase curve. Okay, so I'm going to go ahead and draw my axes. Omega. Wow, that's pretty bad there. Phase in degrees. Okay, so we're going to hit 180 up here. And go ahead and mark 90, 0 degrees. And down here, I'm only going to worry about negative 45 and negative 90. So pretend those are all symmetric. All right, so here's what's going to happen. I'm going to be interested at 8 radians per second, right? I have my simple pole, 8 radians per second. And so my phase, it would start at 0.8 radians per second. And up at 80 radians per second, it would have flattened out at negative 90. So it's going to look something like this. Negative 90 degrees at 80 radians per second. It's going to look like that. All right, so that's kind of what that's going to look like. And the that's for the simple pole at 8 radians per second. The constant gain has no phase, has zero phase. I shouldn't say no phase. The phase is 0. And then I got to deal with this quadratic 0 with no damping. So what's going to happen there is the phase is going to also start out at around 0. And, well, I got to mark first where it's going to go. It's going to go out to 0.5 radians per second. So I'm just going to mark that here. Okay, so I'm going to say that this is going to go, it's going to come out here. And then at 0.5 radians per second, it's going to pretty much just jump instantaneously up to plus 180 degrees. And then by itself, it would be flat. Okay, so I'm going to just mark this as a discontinuity. Okay, so those are the two phase curves. And then I just got to do something that looks like a composite of that. Okay, so this discontinuity is going to play a big role here. So my phase is going to come out at roughly 0. And then it's going to jump up. And I'm going to go ahead and fill that line in just to make it obvious that it's there. And then it's going to stay up pretty high until we get to 0.8, and then it's going to start rolling off, and we're at plus 180, and this negative 90 is going to compensate for that. So basically I'm going to roll off to something that's going to land at about 90 degrees, and it's going to stay there. So that's what the composite phase is going to look like. All right, so again, kind of a freaky looking thing, but that's what's going to happen with this because of this quadratic 0 with no damping. So I hope these examples were helpful. There's a lot going on here. So again, practice this kind of stuff. I'm going to give you the opportunity to do some more practicing with this. And then we're going to move on to this thing called the Laplace transform pretty quickly. So thanks for listening. Have a good day.